An intro. Thanks everyone for joining us today. My name is Zach Allison with ATS. I've been the host of these ATS universities for a few years now since we started the online program. With me today is Owen Dwyer from SMS, our partner who is very specialized and knowledgeable in the corrosive waste and acid neutralization field. That's going to be the topic as we go through today. We'll be looking at the code surrounding it. We'll help go over how to size and select the right products. And of course, we'll have some Q&A. On that point, we do have everyone muted upon entry, kind of standard practice these days. But of course, we do have our Q&A and chat fields open. We keep everyone muted simply because this is being recorded. It will be available on the ATS University portion of our website for reference in future use. And I think we'll have a sizing guide available for download there after this seminar as well. So I guess without any further ado, I'll pass it over to you, Owen. Thanks for joining us today.
My pleasure. Thanks for the invite, Zach and Rebecca. Welcome, everybody. I'm here in Whitby, Ontario, and we're just going through a little bit of snowmageddon here shortly. So it's noon here, as Zach said. Thanks for joining us wherever you are across the country. Thanks for carving out some time. I'm Owen Dwyer with SMS, Smiley McAdams Summerlin out of Whitby, Ontario. I am the national sales manager for SMS. I've been with the company for going on 10 years. And prior to my joining the SMS team, I was with IPEX as a technical rep for them for Eastern and Northern Ontario. And I currently sit as the acting president for the local ASPE Greater Toronto Area chapter. So that's a little bit about myself. My background is in the sciences and biology. So I got into sales, I guess, connect the dots there. But anyhow, today's topic, as Zach had mentioned,
just one quick point here, Owen. You mentioned the ASPE GTA, and it got me thinking back to a piece I forgot in my intro, and Rebecca would have given me trouble if I left it out. So for any of the engineers in Ontario, and I guess any other provinces that do require you to track your hours on learning, Professional Engineers Ontario this year launched the PEAK program, and we will have certificates available after this if you need your hours for CPD. So we'll be sending out that certificate of attendance. It's part of a new process going on so that we can get these out. So if it takes us an extra day or so to get it out, please forgive us, but we will have those certificates of attendance available so you can submit it for your PEAK program hours. Sorry about that. Thank you.
No problem. Thanks, Zach. It's it's important to point that out. Topic of today, corrosive waste, which includes pipe and fittings, where and when. It's mostly code-based, and as well, I'm going to touch on neutralization, which obviously is a part of the corrosive waste system. So the agenda, we've done the introduction part. I'm going to go through the national codes for corrosive waste. There's 3 piping components. There's plastics, there's borosilicate glass, and high silicon iron casting. I'm going to talk about unit value comparisons, typical applications, how to select the material. Sometimes it's kind of not so clear, but hopefully I can clarify that for you today. Neutralization and dilution, comparing the two. The words are used kind of interchangeably in the code, but I'm going to talk about that and have you understand the differences and the importance of thinking neutralization versus dilution. We're going to talk passive and active neutralization and the different options available, and then we'll just do a quick summary. So with respect to the code, so the national code, regardless of what province or territory you're in, is identical and verbatim when it comes to actual corrosive waste piping system. So what does the code say? As per the National Plumbing Code 2281, any pipe and fitting to be used for drain and vent of an acid or corrosive waste system shall conform to. So we know in the code, shall means must. must conform to, and you have A, B, or C. A is the ASTM A518 corrosion resistant silicon iron casting. It's a mouthful. B is the borosilicate glass pipe and fittings. And then C, you have your CSA B181.3. Polyolefins is a fancy name for polypropylene or polyethylene. That's part of the polyolefin family. And PVDF, polyvinylidene fluoride. So I just on the left there is the 2281 kind of zoomed in, but it's verbatim taken from the section of the code there on the right. So in the previous slide, when it talks about pipe for venting, for drainage and venting. So this is the part 2553 in the same discussion where it talks about venting. Venting for drain piping or dilution tanks conveying corrosive waste shall, again, means must, extend independently and terminate in outside air. See Article 2577 for sizing, which I'll go to in the next slide. But just I'm just kind of touching base on the venting because it is an important thing to remember that it's not only the piping on the drain side, but it's also the venting. It's very specific because if you have corrosive vapors that condense back in through the vent piping, it's going to turn back into a corrosive liquid. So the section points to the separation of the corrosive waste and venting from the sanitary. And this is the 2577 portion where it talks about specifically the second point here, the size of every vent pipe for a sewage sump or dilution tank shall be not less than 2 inches, but not need to be greater than 4. So that's taken from, again, the code section to the right. Essentially what that means, normally speaking, venting of any system is typically 1 trade size less than the maximum size of the piping system. But it's in this case for the venting of a dilution or neutralization tank, it should not be less than 2 inch, but need not be greater than 4. So sometimes you'll see some manufacturers, and again, this is very specific to our Canadian code. Our counterparts and neighbors to the south of us do not have these same regulations. So you may be familiar with some under the sink neutralization systems. These units all have to have a vent as part of a neutralization or dilution system, and the minimum vent sizing is 2 inch. So that's kind of the nuts and bolts of why we're going to talk about this today. And as you see from the first, the 2281 of the national talks about A, B, and C. A was the dur iron or high silicon iron casting. B was the borosilicate glass, and C was the plastic. So I'm going to start with the high silicon iron casting. It is classified as a non-combustible pipe. For those of you that are in attendance that have been around in the industry for as long as I have or longer, you may be familiar with the name dur iron. It was manufactured by Flowserve. Flowserve was out of, I believe, New Jersey or New Hampshire, somewhere in the eastern part of the U.S. And it was a no-hub style system that went together using mechanical type connections with a kind of a Teflon coated rubberized fitting with a stainless steel jacket, etc., that you could see in the image there. But it's discontinued. So it hasn't been amended or it hasn't been removed from the code. For any of you that have been involved with any of the code changes, it's not a quick process. So hopefully in iterations of the code to follow, the borosilicate, the dur iron reference will be removed. As of April of 2016, we were contacted by Flowserve saying that they were going to discontinue it. But as you can see in the image there, like old dinosaur bones, every once in a while, a backhoe will bust into a piece of dur iron, and people are scrambling to find out what to do and how to transition. But it was the inception product for corrosive waste over 100 years ago. So basically, it was your standard cast iron with an additional ingredient in there of silica sand, which is the high silicon iron casting. it was very heavy, very difficult to deal with. And from time to time, again, if it is unearthed, all we can do at this point, because it has been discontinued, is to adapt or transition using various, mission couplings, for example, or Dallas specialty couplings. You don't want to use the standard rubber like a Fernco or a standard MJ with a standard rubber. It has to be specific and suitable for the purposes of corrosive waste drainage. So I don't want to talk too much about Duriron because it doesn't exist anymore, but you will see it in the code or again in your travels if you do have a job site that you have specified some plastics or other material for corrosive waste and you do unearth those Duriron dinosaur bones, you need to transition. Borosilicate glass is also classified as non-combustible, and the reason why I'm pointing out non-combustible will make some sense in later slides. Borosilicate glass, so if you think of a laboratory environment, most of the vessels and things that carry chemicals in a laboratory setting are made of borosilicate glass. So the flasks, the beakers, the all of the parts and pieces that you find in a laboratory, all that glass isn't the same glass that you would find in your kitchen cupboard. It's not the thin glass material like a wine glass, etc. It is a very specialized glass. It is the borosilicate, again, that silica sand that gives it again some durability and the chemical resistance. It's non-combustible, so similar to copper, cast iron, etc. It has no requirements for meeting flame and smoke in the building code because it's classified as non-combustible. It is made by skilled tradespeople. So unlike something that would come out of a mold, glass is made by skilled tradespeople where they would take a small section of glass and using a torch and a jig will make a small section of pipe into a 90, whatever elbow, U-bends, etc. So it's it's not a mass-produced injected product. So it is the most expensive of the options for corrosive waste, and some of that is due to the fact that it's all made by hand. The way glass is cut, it's cut internally using an internal diamond wheel. So for all of you kind of CSI fans and seeing a robber or somebody stealing an artifact from a museum, how they cut through glass using a diamond wheel, similar process, but what you have with the borosilicate glass is you're creating a score using a diamond wheel on the inside of the pipe. Once that tool is removed, a torch is involved. So that torch on that score creates a thermal shock, which separates the glass, the two glass pieces. So it is a skill. They still have it as part of their CFQ for the plumbing trades here in Ontario. I don't know about other provinces, but it is still, how do you cut glass, et cetera, et cetera. It's on the plumbing certificate of qualifications here. So a glass piece of pipe has beads on the end. I'll go to a previous slide here. You can see that all the fittings have a flare or a bead on them. One more slide. You can see on the left-hand side there, you'll have a piece that's cut. That's a cut piece of glass that's plain end. And on the right-hand side, you'll see a piece of glass that has the factory flare or the bead is what it's referred to. So you have a piece of pipe that has a bead on both ends, a fitting that has a bead on both ends. But when you cut your piece of pipe, now you're left with one end that's beaded and one end that's plain. So hence the name of these, the terms for how you join the pipe and fittings together. So again, a fitting to a fitting, you have two beads. You would have what's called a bead to bead coupling, which in the image there on the slide is the thinner unit on the top. And then you have the bead to plane. So the bead would be either the glass end or a fitting end, and the plane would be the plain cut piece of glass. So that's the bottom image there. The white that you see is Teflon, and the black is a rubber that kind of holds it all together. This is just a line, kind of a hand sketch of what the bead to bead and bead to plane looks like. And just a note on the bottom for the beads of plane, glass is made to IPS dimensions. It's iron pipe size, which means it's suitable for connections to plastics that are iron pipe size, which is the next material that we're going to get into. Or so basically, it's a DWB or Schedule 40 type of iron pipe size dimension. So that's
That
often
means you're getting the same flow rate for an inch, a 2-inch, glass from Kimax as you would from the IPS standard,
correct.
right?
Yep. So the ODs match essentially. So you don't have to have any special transition. So a bead to plane coupling is often used as that transition to a dissimilar material. So jumping into the C of that A, B, and C is the plastics. So if you recall, the CSA requirement is the B181.3. And what that covers is, again, the polyolefins, which are your polypropylenes and your PVDFs. And they, being plastic, are combustible. So in our world of code compliance, you may be familiar with, and again, I'm drawing on my previous tenure with IPEX, there is a flame spread rating requirement and a smoke development requirement, depending on the type of occupancy of the building, return air plenums, et cetera, flame spread of less than 25, smoke development of less than 50, et cetera. So it still comes into play for corrosive waste. However, back in the mid 1990s, there was only dur iron and glass as options for corrosive waste. So I believe it was 96, 97, the plastics were introduced into the market, specifically polypropylene first. And this is the section of the code that was introduced to create an exemption for polypropylene in the code. And it reads that polypropylene pipes and fittings are permitted to be used for drain, waste, and vent, for the conveyance of highly corrosive materials, and for piping that's used to distribute distilled or dialyzed water, so which is your RO and DI water in a laboratory setting, in a hospital facility, in a building required to be non-combustible, provided A, the building must be sprinklered. So for example, if you're doing a retrofit on an existing school, an elementary school or a high school that used to be a geography room or an English class, and you're now retrofitting that building to be a science lab, if that part of the school does not have sprinklers, polypropylene is not permitted. You have to have a sprinklered building for this provision to take place. And why that was done is, as you'll understand later, it's basically cost. So if you think of where a lot of these labs are, they're in hospitals, they're in universities, they're in high schools, and all of these buildings are government funded spaces. And with lobbying to the government, and with the government basically understanding that there's a big cost saving, it did not have, polypropylene, for example, did not meet the flame spread requirement, but it was a very good product to use for corrosive waste drainage because of its inherent properties of being inert to chemical attack. I'll go through that a little bit later. But the point I'm making on this slide is that the building must be a sprinklered building in order for polypropylene to be an acceptable option. If polypropylene can't be used in this purpose, in this example, if the building is not sprinklered, then you have to go with a PVDF product or a glass product. So that's the importance of this information here. So there's essentially there used to be three manufacturers in North America for a corrosive waste product that have certifications to that CSA B181.3, and now it's down to 3. So Zurn was a product that was manufactured in this environment, but they stepped out of the acid waste and corrosive waste market, I believe in 2020 or 2019. So everyone has their variations, their different mousetrap tools, product, etc., but they all have to comply with that CSA standard, regardless of what widget it comes with or how it's joined. That CSA is your design criteria. So I would encourage engineers to stay away from specifying manufacturers' names when it comes to corrosive waste and kind of stick towards either the borosilicate glass, which is the ASTM standard, or on the plastic side, make sure that it's a CSA. And the reason I say that is because some of our US counterparts will come into the picture saying, hey, we have this PVC DWV acid waste system or a CPVC acid waste system, etc. If you look at those in context of our code, they must comply with that CSA 181.3, which is again polyolefins or PVDF. The other plastic materials are not, they're not a part of that as our code is written today. So an acid waste system, when we talk about polypropylenes and PVDF, you'll see references to flame retardant polypropylene, non-flame retardant polypropylene, and obviously the PVDF material. Some manufacturers have variations in color. You'll hear brown line or blue line or Enfield, lab line, plenum line, et cetera, et cetera. So regardless, again, of those names or nomenclature, it comes down to a requirement of polypropylene is permitted in the building if it's sprinklered. You can't put it in a plenum because it doesn't meet flame and smoke. PVDF meets flame and smoke, and it can be used in lieu of polypropylene if it's a non-sprinklered building. These are the things you have to keep in mind when you're specifying and looking at corrosive waste on the plastic side. Electrofusion and mechanical joint. So because polypropylene is inherently inert to most chemicals, it's not susceptible to softening and joining with solvent cements. So like a PVC, DWV, or CPVC, or ABS, all of those other thermoplastics can be joined using chemical welding or socket and spigot chemical joining. Polypropylene and PVDF cannot be joined using chemicals because, again, their inherent nature of being inert to those chemicals. And again, you just think of if you were purchasing a chemical, for example, like bleach, it's going to be sold in a polyethylene or polypropylene, a polyolefin type of a container. And the reason for that is that it's inert to that chemical. So a winded way of saying you can either join polypropylene by way of fusion or by way of mechanical joint. And again, I want to reestablish the fact that we're specifically talking DWV in this presentation. There are polypropylenes and PVDFs used for pressurized, like pure water distribution. I'm not talking those. There's different beasts altogether. But polypropylene is generally available up to 12-inch for DWV here in North America. Some manufacturers claim that they have up to 16-inch, but that's not something that you're likely going to find on the ground or readily available here in North America. Jumping into a unit value comparison. So if glass is a control factor with a unit value of 1, so just for simple math, if you had a $1 million pipe and fitting takeoff value for a glass job, PVDF would have a unit value of 0.75. So it's about 25% less than glass, depending on the pipe and fitting configuration. And polypropylene is 0.35. So it's almost a third the price of glass. And you can see why those special provisions were made or intended in the code, is to allow for something that is that much lower in overall cost. And if I can kind of bring you back to the history, polypropylene was in the picture before PVDF. So polypropylene had a direct comparison to glass at that time. So that $1 million school renovation that you had no other choice. Now polypropylene, with that special building provision, you're able to get a material that's a third the price. And you can see from that last point there why Duriron went the way of the dodo bird. It's 3.5 times that of glass, so 10 times more than the polypropylene option that was introduced in the late 90s. And again, it just makes sense to all of us as to why that's now no longer available. So general code requirements for corrosive waste. We talked about suitable for the purpose. And this is, I bring this to your attention, the 2211, specifically the second point, materials and equipment used in a drainage system where excessively corrosive wastes are present shall be suitable for the purpose. So this goes back to when I said, when you're doing a transition, you unearth the dinosaur bones of dur iron. Don't just throw a standard rubber Fernco coupling on there and bury it and expect it to last. So there are materials that are designed for those transitions, and they are made and intended to be specific and suitable for the purpose. So again, because this is corrosive, highly corrosive material, you want to make sure that all your parts and pieces that are being used for this application are again going to stand the test of time and suitable for the application at hand. Transition accessories, there's again, that's an image of a Dallas specialty coupling. There's the FKM mission couplings there in the center, and then there's different transition adapters. So male, female fittings, bottle traps, cup sinks, etc. So there's a whole slew of variations with respect to transitions and accessories. But just keep in mind that it has to be suitable for the purpose. Dilution tanks, neutralizations, and solids interceptors are all a part of it. You'll see on the image on the right-hand side, you have your corrosive waste piping coming into an interceptor that sits on a stand. You have your neutralization tank that's vented at the 6 o'clock facing us. And then downstream, you can see a little bit in the picture there that looks to be cast iron that's that has been insulated with an insulation jacket. So downstream of the neutralizer, you can use traditional materials, PVC, cast iron, copper, whatever's suitable. So a pH monitor is also a good thing. I'm going to go into neutralization in the next couple slides, but this is a part of the accessories to point out. pH monitoring systems. Where are we going to see these types of applications? Again, I mentioned high schools and hospitals and universities, but you're also looking at industrial applications. So if you have chemicals in an industrial application, be it a photo lab or a plating company, pharmaceutical production facility like an Apotex or GlaxoSmithKline or some of those facilities, and food and beverage. Food and beverage comes into play with respect to predominantly cleaning. So they will use either acids or caustics to sanitize and clean their equipment prior to starting up the next batch, if you will, or in between shifts, etc.
Yeah, I know one of the applications that we don't show on there, but it comes up regularly in our discussions is like the battery replacement for, say, a forklift or anything like that.
Right. Yep.
That one's come up pretty regularly as well, and that could be a warehouse, all sorts of different applications. So
yeah, that's an excellent point, Zach. And on that note, so essentially what Zach is referring to is any large facility that's got large forklift batteries. You either have a facility that's got one or two forklifts, may or may not warrant what we're discussing here. But if you've got a Lowe's or a Loblaws or a Sobeys, a massive distribution warehouse where you have forklifts with massive batteries, you have a battery washing station, all of that. Sometimes while the battery is being charged, it will overflow. What's in those batteries is sulfuric acid. Or, for example, if you have a breach of one of those batteries, if the battery actually breaks, the housing breaks, now you've got sulfuric acid all over the floor. Essentially, what you want to do is you want to have the ability to wash it down with water that's available into a drain that is dedicated to that area that has a neutralization system that separates that sulfuric acid from connecting to the sanitary system. So thanks, Zach, for bringing that up. It is very, very common these days to see neutralization systems for those applications. So why are we talking corrosive waste piping? Because you need to. You have to comply with regulations, as I mentioned before in the code. Shall in the code means must. You have to have the chemical resistance, whether it's polypropylene, PVDF, or glass. You have to make sure if it's an industrial application, is polypropylene suitable for the chemicals? Is it suitable for the temperatures, etc. So you're trying to look for the completeness of the line. So again, is it combustible, non-combustible? Are there plenums or vertical shafts in the building? Is it a sprinklered building, etc.? And these aren't just your standard off-the-shelf products that you'd see at most wholesale distributors. These are advanced engineered materials for this specific application. So again, don't expect every wholesaler to have this on the shelf. So Zach, if there's no questions on the piping right now, I'll jump into the neutralization portion of the presentation.
Yeah, we can pause for a second. I haven't seen many questions coming in. I think that's because it's relatively straightforward, right? Like the discussion so far is just showing this is the code, these are the important aspects of it,
right.
And these are some of the options you have to meet it. But even when you reference back to the how you would suggest an engineer write a spec, it's more of a code-based spec versus a product-based spec. And I think that's because specifying the codes that are referred to, they have different CSA ratings, like you mentioned, and those are going to be the more important parts to meet. And I think it's good to point that out, because we're going to, in the second half here, have a differentiation there, right? So I haven't seen anything come in yet. So I guess we'll let you dive into the neutralization, because I think seeing that juxtaposition is going to be interesting here.
Yeah, and it's again, as you mentioned, the piping side of it is pretty straightforward. So you've got a sprinkler provision for polypropylene. PVDF is the plastic that's for flame and smoke ratings in lieu of not having a sprinkler building. And then you have your glass, which is your non-combustible option. And obviously keeping in mind that it's the most expensive, but we'll jump into neutralization. And in this process, there will be a quick recap. So the code, again, is very specific when it comes to requirements for corrosive waste pipe within the building, within that building envelope. So again, the 2281 talks about the A, B, and C of the pipe, combustible pipe restrictions, which was the 31516 with the sprinklered building. The 3643 I didn't talk about, but that's your general plenum requirement. That is kind of it would trump the sprinkler thing. If you have any product in a plenum, it must meet the 2550 flame and smoke, and your venting requirements in 2553. So it talked about extending independently and terminating in outside air, as well as having a minimum vent size of 2 inch, but need not be greater than 4 with regards to a neutralization system. And what piping also takes into consideration when there's an inspector in the building, for example, you talk about vertical shafts, talks about fire stopping, it talks about slope, etc. So this is very, very specific. There's a lot of attention spent on the piping side within the building. However, when it comes to neutralization, this is the part that I want everybody to understand. We know that you're collecting all of this nasty stuff within the building because there's special provisions for a special piping that says thou shall use either A, B, or C. Now you're collecting all of this stuff. What do I do with it? You just can't put it into the sanitary system. So in 2444, it says where fixture or equipment discharges corrosive or acid waste, it shall discharge into a neutralization or dilution tank that's connected to the sanitary drainage system through a trap or indirect connection. But most importantly, the second part here, neutralization and dilution tanks shall have a method for neutralizing the liquid, period, full stop. So it doesn't tell you how big it is. It doesn't tell you what it looks like. This is an engineered design system. So you as the designer have to take into consideration fixture units, location, is it above ground or below ground? There's a lot of things that go into the planning and designing of a neutralization system, whereas as Zach mentioned, and I pointed to, the piping kind of takes care of itself as long as you pick the one that's most suitable for the building. This is coming down to what's most appropriate and sizing it for the actual incoming effluent. So in general, we use the word corrosive, but what we're essentially talking about is sewer use bylaws. So every municipality will have a listing of what it is you're allowed to discharge. And this topic is very, very specific to pH. Full stop. We're not talking about biosolids. We're not talking about, kill systems. We're not talking about petroleums or anything like that. We're addressing pH, and that's all we're addressing. Most municipalities will have it spelled out right in their sewer use bylaw, saying, not permissible to discharge anything lower than a pH of 6 or greater than a pH of 11. So that's your window. If you are outside of that permissible window, you're corrosive. So this is where neutralization comes into play. So as I mentioned in the code section talking about neutralization, they also mentioned the word dilution, and they seem to interchange those two terms. And I want to be very specific and kind of give you a little bit of background as to what the main differences are. And dilution is not the solution to pollution. And I say that because on the onset, I said my education is in biology research. I used to have a professor that when we were done our experiments, we would essentially turn the cold water tap on in the lab. And no matter what we had in our beaker, we just poured it down the sink and left the water on for 5 minutes. And that's the term he used. The solution to pollution is dilution. So, and I shake my head thinking back now, if I only knew. But anyhow, neutralization is the way to think about what we're trying to deal with, not dilution. Most municipalities will actually spell it out. That's why the parentheses dilution is not permissible as a form of neutralization. It's in parentheses because that is a hyperlink, and I have not had success in presentations clicking hyperlinks, so I'm going to just tell you most municipalities have that verbiage in their bylaw that says don't use water as a permissible or as a form of neutralization, because it's a waste of natural resources. It affects the downstream waste facility with excessive volume, and it's non-compliant, as I mentioned, to most sewer use bylaws. And it's that kind of NIMBYism approach to the problem, where just say you have a pH monitor that says, hey, we're in an alarm situation where we have a pH of 5, and you turn a bunch of water on. You don't actually treat that water. You're flushing that pH 5 out of your building and into the municipal system. So it's not appropriate as far as thinking of dilution as a form of neutralization. So if I can get you all to jump back in time on the time machine to grade 7 science class. So you're familiar with this chart. So every pH level represents what's called a decade unit. So there's a 10 times difference in the degree of alkalinity or acidity in each of those numbers. So as an example, a pH of 6 is 10 times more acidic than a pH of 7. And the difference between a pH of 5 and a pH of 7 is 100 times. So that jump, or that decade unit, is what you have to wrap your head around. Because if you think in terms of dilution, what that means, so if I had a liter of acid that had a pH of 1, so for example, it's a 1 liter beaker of sulfuric acid or muriatic acid or whatever the strong acid was, and I wanted to neutralize that acid to become a pH of 7 by way of dilution, I would have to mix that 1 liter of acid with 1 million liters, if you follow the amount of zeros, of clean fresh water to neutralize that 1 liter of acid. So just think of what that means. So that's 1 million liters is 50,000 5-gallon jugs, or enough water for 15,000 showers, enough water to fill a 25-meter swimming pool. So you don't think of dilution as a way of treating the incoming liquid. When you do want to consider dilution, is very specific, and it warrants dilution, is dialysis waste. So if you're looking at a hospital that is predominantly focused on dialysis, you will have a corrosive environment. So dialysis waste, it is a concentrated uric acid, and it's generally falling between 4.5 to 5.5. So it does require some treatment. If, for example, your municipality has a limit of 5.5, you don't need to do anything with it. If, for example, your pH is 4.5 you may want to tie it into the last, the last connection going out of the building, and treat it by way of dilution twofold. One, because it's very, it's a viscous liquid. I don't know if you're familiar, those that are familiar with dialysis waste, it's quite viscous. It's like almost like a latex paint, and it would absolutely be detrimental to a calcium carbonate limestone neutralization system, essentially pouring latex paint over the stone so the stone doesn't have contact with the liquid. I'll touch base on the calcium carbonate shortly. Just going to double check time here. So what we do is dilution approach for dialysis waste. And how we do that, we have either push button controllers that inject liquid into a tank, or you have a flushing floor rim type of a scenario. But this is dilution for very specific application, which is dialysis waste. So the proper and most common way of thinking of neutralization is either passive or active. And a passive system is what you would typically see. It's limestone, and those systems are calculated based on a specific duration of time that the liquid has in contact with calcium carbonate limestone, which is an alkaline substance. And then you have an injection system, which, again, going back to science class, if you have an acid and you mix it with a base, you get neutral. If you have a base and you mix it with an acid, you get to the neutral side of it as well. So basically you're injecting an opposite, so to neutralize it prior to discharge. This is your standard gravity flow system. As I pointed out in the previous slide, you have your interceptor, you have your vented neutralizer, and downstream on the right, you can see that it's a cast iron connection downstream. So this is the meat and potatoes of neutralization. How do you size a passive neutralization system? The typical calculations and industry standard forever has been to use a minimum of 1 gallon per hour per fixture unit in your system. So fixture units, very similar to when you're sizing water lines. Fixture unit counts are available through the National Building Code hydraulics load for fixtures in 2493. So counting up your fixture units, whether it's a number of sinks, your eye wash units, floor drains if they're connected to the neutralizer, emergency showers, if you've got glass dishwasher washers in the laboratory, et cetera. So all of those have an associated fixture unit. And this is a snippet of the 2493, of which here is a very typical example. So you have a lab and you've got 20 lab sinks. A lab sink under that 2493 fixture unit load chart is equivalent to 1.5 fixture units per sink. Excuse me for a second. And this might have, for example, 3 4-inch floor drains. A 4-inch floor drain is 4 fixture units times 3 of them. You have 12, an emergency eye wash unit, et cetera, et cetera. So you add up all of your connected fixture units to your neutralizer, or that your neutralizer would encounter. In this example, we come up with the number of 57. So that's your minimum volume that you would require to hold for a 1 hour period. Again, going back to the calculation, 1 gallon per hour per fixture unit in the system. We normally like to allow a safety or diversity factor, whether it's 10 or 15%. That's completely personal, or what you've been designed. Sometimes you design in phases. So maybe you want the neutralizer to be oversized for the first size. It looks way too big for what you've got coming into it, but it makes sense when the building's phase 2 comes into play. So 57 times 1.1 or 1.15, you end up with in the 62.7 to 65.5 of actual liquid capacity. That's the important term, actual liquid capacity. So that's 65 gallons. That's functional. What is your functional capacity? So I use this image here. There's a hole in my bucket. So my analogy is you have a 5-gallon Home Depot bucket. it will hold 5 gallons of liquid. But if you fill it up with rocks and you put a hole in it a third of the way down for your inlet, your outlet, and your vent, you can't hold 5 gallons anymore. So don't refer to it as a 5-gallon bucket. Refer to it as what it's functionally capable of handling. How much liquid will actually be in that bucket once you add the stone and your inlets and your outlets. So for example, our 57 gallons times 1.1 or 1.15 brings us into an AN65. An AN is just a term for an acid neutralizer, and the 65 is a term for its functional capacity. You can see 3 columns over that it's 36 by 48. It's highlighted in blue is its functional capacity, but in white in the first column to the right there, it says 142. So that's that 5-gallon bucket analogy. So why specify 142 gallon sump? It's not ever going to see 142 gallons. So specify and think of it as what it is that you're actually wanting to hold, because you've just completed a fixture unit calculation. The most important thing is detail when it comes to specifying neutralization. Put the dimensions in there. So pi r squared h, 36 by 40 by 48. You have your volume of a cylinder. By the time you do your conversions, that's going to give you 142 gallons empty, or 65 as a functional capacity. So the functional capacity, again, as I mentioned, you have all of these, this limestone that's in your system, they displace the liquid. So typical rule of thumb is to use a 50% displacement, and that's based on a 1 to 3 inch size rock versus something that's small. You're not looking at something that's a pebble size, you're looking at actual stones. And you see upstream of that, you'll see the interceptor, which I'll go through momentarily. There's 2 types of systems that you have to consider. Is this going to be sitting on a finished floor above the ground? Is there any room limitations? The tank may be placed in series to meet that requirement, but the picture to the right, for example, it fits in the room nicely. You've got a couple boxes of limestone on the side as subsequent charging as needed. And this, for example, on the right, you'll see the small interceptor on the stand, and then there's 2 tanks in series. So it leaves this first tank, enters into the second tank because of floor space, or maybe there was a door restriction. So I say that to people, make sure if you've got a retrofit application and all of your doors accessing this room are 34-inch doors, but you've specified a 48-inch diameter sump or tank, it's hard to fit a 48-inch diameter tank through a 36-inch door. So this example on the right was likely the case. I don't remember the specifics, but it was likely a Canadian job just based on the Tim Hortons cup sitting by the interceptor there. Anyhow, this was a 2-tank in series system. As long as you have the appropriate dwell time for that corrosive liquid coming in, you're fine.
So that actually ties into a question that just got brought up in chat, because you mentioned the dwell time there. So I guess just to reiterate, we had talked about how the fixture units lead to your total gallon per hour flow time. That say 65 gallon per hour using our example means that you want a 1 hour contact time. So 65 gallons of functional storage is what we're looking for.
Right.
So with the example that you gave there, if the max size that fit through your doorway was, use round numbers, 100-gallon tank, 100 gallons of functional capacity, but you had 200 gallons per hour, you could use the 2 tanks. That's what you're saying, correct?
Correct. Yep.
And just as another point, I know we are coming up close to the hour here. For everyone on the call that maybe has a strict time stop, thank you for joining us. I'll say that now early because I do anticipate we'll probably have a few more questions. We might run a little bit over time. I appreciate you spending the time with us that you could today if you do have to leave. But we're going to continue going on, and the recording and all the links and resources will be available on the ATS University in our Ask the Expert section after the seminar. So in the future, and we'll have links sent out to everyone so that you can review any of the content and get into the recovery of the presentation.
Thanks, Zach. Then thanks for the time reminder. So I'll kind of push through here. So you have your above grade or below grade systems. What you have to take into consideration with the below grade system is, again, you want to maintain that functional capacity, but you also have to take into consideration your developed length. So as you go farther away, you have to comply with your slope of your piping. So if, for example, the tank was in this room, but now something's happened on the job and you have to move the tank 100 feet away, you have to now reevaluate and reconsider that tank's location and sizing, because you have to now take into consideration your inverts. And again, there's that tip: don't forget to consider door openings for existing buildings. So that covers the passive. Passive neutralization is very specific for acids only. So predominant acids, acid effluent. When you get into active injection is when you're going to have something that's predominantly alkaline, or you might see both alkaline and acid. So very rudimentary picture here. You've got an untreated liquid coming in. You've got dosing pumps of either an acid or a caustic that's being mixed with the mixer. You have your pH controller, level sensors, etc., and you have a treated effluent that goes out the building. So how do we size those tanks? The gravity flow is based on fixture units, and these are estimated with maximum flow capacity. So you have to know what your estimated GPM flow rate is. We take that number, multiply it by 10 or 15. I know ASPE likes to use 10. We at SMS and I over the years have used 15, because what it does is it gives you a little bit more volume, but it also allows for a slightly lower reagent concentration as far as the injection reagent. So different different injection neutralization systems. You have the skid type on the left. All the components are going to be the same. You have a controller, a dosing pump, a mixer, you have your tanks, you have spill trays, etc. The one on the right, I believe, was Mount Sinai. And you'll see that there's the dosing tanks in black on the bottom. You see the dosing pumps, pH controllers on the wall. Then downstream, you can see the agitator on top of the tank in the back. Different various injection systems. Interceptors are very important for these. You don't want any solids to get in these systems. This is just giving you an idea of what an injection system would look like, and the specific, these are all designed. These are all, again, as I mentioned, these are engineered systems based on an anticipated flow rate. And it's up to us in this industry to scrutinize the submitted equal alternates, because ultimately the inspector sees the magic box. They know that they're supposed to be a neutralizer, but they have no real information or background as to what it's supposed to look like, how big it's supposed to be. They're not going to scrutinize it based on its construction qualities, etc. So that's up to us.
So, and I guess that level of scrutiny is something, just to harken back to the beginning of the neutralization section. We talked about how, the two pieces in the code was that it must be neutralized and the neutralizer must neutralize. So your particular spec as the engineer is what you have to make sure any alternates are meeting. And this is one of those pieces where there's not a lot of options that are all truly equal. You may have, someone could submit a garbage can full of limestone and call that equal to an engineered product, and it's up to the engineer to properly review and spend some time on this engineered equipment, as you said.
Right. And that's a great point, Zach. And thank you for the garbage can analogy. I know you've seen my presentation before. So
a skull and a line or two.
So essentially, that's it exactly. So when a manufacturer of a rotationally molded tank sells a tank, they don't know if it's collecting rainwater, if it's being used to store dog food or to ship bird seed. they have no idea. They've made a rotationally molded tank. It comes with the lid. Here you go, Mr. or Mrs. Customer. Off you go. When we receive a tank from a supplier, we modify that tank for the purpose at hand, which is acid waste neutralization. So in that, you have your above grade tank. You have to cut the top off of it. You have to kind of make a gasketed connection using stainless steel bolts, etc. There's a little line drawing of the of what you're looking at. And then you have a below grade buried application. So you're going to bury a tank below ground. You want to beef it up because people are going to possibly walk on it. So you can see this insert has the same gasket, but now that top of the tank is beefier. And there's an inset. What do you do with the nut, the receiving nut on the bottom? In this case, it's welded right into the bottom of that tank. And again, these are all the things it's designed. It's built for that specific application, not to hold bird seed, etc. Non-skid aluminum top. So here's an equal, for example. You say, yeah, it must have a 1-inch top. Okay, well, this has a 1-inch top, but because the sides are so flimsy, they had to use a foam gasket. And how do you, I don't know how to even describe that receiving mechanism. It looks like a something that you would use in woodworking to hold a bolt against the back end of a piece of wood. But anyway, so this is what people submit. And as Zach pointed out, will a garbage can full of limestone neutralize? Yes, but in a $500 million hospital application, you don't want to get. I'm just going to play this video here. This is the manufactured tank as supplied with the flimsy lid. Again, they don't know if you're collecting rainwater or what, but this was turned into a neutralizer and interceptor. But what they don't have is a seal. So this is copper pipe in this small mechanical room housing the neutralization and sediment interceptor, where the vapors were escaping the tank during the whole time. I'll just play that again. You can see how flimsy the lid is. Why would you want to try to bolt that lid down to create a seal? There's not enough substance to that lid to create a proper seal. So that's Zach's analogy, and I used that before. If you don't scrutinize it, the contractor is going to want to save himself or herself $1,000 if they can by putting in a garbage can and a bunch of rocks and call it a neutralizer. So they're not all created equal. You're doing a design, you're creating something that is going to be either buried in place in the ground. It's a permanent embedded receiving hardware, the neutralization tank vent sizing. Does it have a pH system on it, etc.? So these are things that you need to make sure that are there before you accept alternates for these types of systems. So that's neutralization. I'm going to briefly touch on interceptors. Interceptors are not a part of the code, but what they do is they protect the neutralizer from having any particulates cramming into the bottom of that interceptor's dip tube. So you can see here on the right-hand side, if you didn't have this liquid being forced to the bottom of the stone, you'd have what's called laminar flow. It's just going to go in, go out. So every neutralizer has to have this dip tube. If you didn't have the interceptor upstream and there's broken glass or whatever ending up down in here, you're going to have GFL Environmental have to come in and remove 1,000 pounds of stone in order for you to clear a small little clog in a 3-inch or 4-inch inlet pipe. This is what you're going to see. You're going to see broken pieces of glass, pipette tips, or pH litmus paper strips. More often than not, they inadvertently get dumped down the sink. pH litmus paper strips now are made out of plastic. They won't dissolve like in the old days, made out of paper. So think of it as a system. It's a standalone system. It's upstream of the connections to the sanitary, and more people that are aware of this type of a system, the better. And sometimes it comes down to educating the end users as well. Don't, you're not just putting anything down these sinks because it's not going into the standard sanitary stream. There's an interceptor or a neutralizer before that. So
yeah, again, like that's not necessarily dictated into code, but it's similar to a backflow. The manufacturer would likely recommend a strainer upstream of it.
Right.
With this intercept or with this neutralizer, recommending essentially a strainer,
Right.
but the interceptor upstream.
Absolutely. Yeah. And it's best practice is what it comes down to. And the type of job is it a high school? Is it a university? Or is it an industrial lab? If it's an industrial lab, maybe you're going to have less Tupperware dishwashing of the croutons in your salad left over in the sink, whereas you would see that in a high school or in a university, for example. So the interceptor is not a code requirement, but it comes into play in a lot of these applications. So on that note, I know time wise, I kind of
Well,
push
so
my.
yeah, we'll kind of pause and take a look for any questions here. And while we're doing that, I will, if you can stop sharing for a second, I'll show. We mentioned how one of the big pieces with this equipment is making sure that we have a proper specification. And as you may know, that's where I come in with our ATS spec tool and show you just very quickly how you could find and specify this product. You'll see I've already put together a project here as part of my preparation. But if you were looking to start a new project, you could either create a new spec, create a new project, enter your information, test AN system, tab through, select your locations, select your locations, yada, yada. And then select your application. You could select a lab, you could select your high school, anything like that. And then you would have your project created. From there, you'll be able to come in and add products into the project folder. You can also add separate tabs. One very quick thing, if it's been a while since you've checked out the system or seen the updated presentation, I think Rebecca and I did this, covered this topic back in December, but we do have a couple of changes. You'll see the category search is here now. Well, you can still search by model name or number. And then we've added a handy feature, these little pins, so that you can pin your favorite product categories. So backflow, anti-scale system, pumps, water heaters. I could search for neutralizers and pin this to my favorite now, and it'll show up here. And then if you're selecting it regularly, you can just jump right in and find the products that you're searching for all the time. Here you can see our AN and SI system with the functional capacities as we noted. So if we wanted that 65-gallon functional capacity, we mentioned our pH monitoring system. Maybe this is a recessed application with a floor tank cover, and if it's really below grade, we may need the extension. I'll select my extension type, and then you can see as I selected the flow rate, our configuration recommends the appropriate model number for the sediment interceptor. If you want to double check any of this information, the manufacturer spec sheet goes right from this little button here, where you'll see the SMS information on their interceptors and the sizing and all the different pieces that they have on their manufacturer spec sheet. We can add this to drawing. And if there was any other selection steps that were needed, it would recommend it here, but this is a standalone engineered system. So we can just hit complete. And we've now added this to our project file. I'll hit edit. I'll call this AN1. You can include a note. Call Owen Dwyer from SMS for custom special pricing. He'll give you a discount. Just kidding. We'll hit save. And then we need to download it off of the system in order to put it into your internal documentations, which you can do in any one of our many formats. We've got the submittal sheet. We've got our product brochures, schedules, 3 different variations of written specs, the manufacturer spec sheet as well, and everything on the system available in Revit. So if I did want to just download the written spec, hit continue, it's going to package that up. As I mentioned, I was preparing to be a little bit behind the game. I've already downloaded a few of these packages. So the manufacturer spec sheet package gives you a nice title page, table of contents, the product that's been selected in the manufacturer spec sheets for all the products that are in your project. That first one, the submittal sheet, is going to give you our typical ATS submittal package, where you've got the marked off boxes of the options you've selected and a bit of a written description. The schedule is going to give you this handy fixture schedule in Excel that you could copy and paste and put into your CAD if that's how you're using it. Put it into your larger schedule system if that's how you're going about it. Mention the CSI 3-part spec so you can get a more code-based 3-part spec. And then I'll flip back here and download our long spec so we can take a look at the long spec as well. And you can see the difference here in terms of the formatting. One other handy feature that in my speed I forgot to reference, our long spec now actually includes an option that was requested from a handful of engineers to exclude page formatting. So if we want to show the difference, you can see the formatting that's included in the document here. It's going to package that up, and that'll remove the tables and columns, so it's easier to copy into whatever format you are using internally at your office. So you can see the differentiation here. We've removed some of the formatting. Doesn't necessarily look as nice, but it is a little bit easier to copy and paste and pop into your written format. So that is the very quick version of the ATS spec demo. Obviously, we could go into a lot more detail, and obviously, even just on this individual topic, there's a lot to cover and there's a lot of questions. So we are running a little long. We'll jump into the questions after this. But if you do have any specific questions and you want to have a deeper dive on any particular applications, Owen and I are happy to jump on a in-person or virtual session to go over your particular questions and your particular applications. I know we've done a handful where we've walked through, they had both the alkaline and acidic effluents. So we walked through sizing and the more detailed options that are available in those engineered systems. So we could certainly do that. But without any further ado, we'll say thank you for joining us today. For anyone that's interested in a couple of questions that came in after the fact, we'll stick around for the next 5 minutes or so. Yep. But thank you once again for your time. Thank you, Owen, for giving us a lot of great detail. If you are looking for the follow-up information, keep an eye on your email. Our team will be sending that out with copies of the presentation, links to the recording, and I believe we have a handy quick size guide that we're putting together as well. That'll be hosted on our ATS University. Keep a lookout for the next session. I think we're diving into some of the new bottle filler and drinking fountain options that are available in the market. So keep an eye out for that and join us next time. For anyone that needs to go and get into their next meetings, we'll leave you now. Owen, we have a couple of final questions here. Should we take into account the acidity of effluent in sizing an acid neutralizer? Or that just be consume the calcium carbonate? Is that included in the 1 hour contact time?
It does generally, but they are, it depends. So if you've got an industrial type application where your effluent is going to be closer to the pH 1, pH 2, like I said, for example, that battery fill type of station, the way calcium carbonate works is it effervesces. So I don't know if you're familiar with, dropping in I'm referring to like camping, for example. You can drop a flavoring disc into your camp water that gives you electrolytes and all that stuff. It effervesces. So the stronger the acid, the greater the level of effervescence and reaction it has. So if you think of a pH 2 coming in, you're going to have a very short ramp of activity, but as that pH changes from a 2 to a 3, remember that's a 10 times difference in concentration. The level of reaction will slow as that pH changes from a 2 to a 3, from a 3 to a 4. So it does take into account that 1 hour dwell time, but again, keep in mind that's a minimum. So you need a minimum of 1 hour per fixture unit in your system. So if you're designing a system that you know or you're aware that you're going to have a very low incoming acid predominantly, then yeah, you're going to have to take that in consideration by adding some more time. So that's
not being the storage, right?
That's a great question. Yeah. So the longer it stays in contact with the limestone, the closer to that neutralization point you're going to get. But you have to also remember that you're not trying to get to a pH of 7. You're trying to narrow down the permissible window as dictated by the municipality. So it could be 5.5. So if you're starting from a 2 and you're trying to get to a 5.5 and you're seeing that you're in an alarm stage, then you might have to increase your neutralizer size.
And I don't think there's any code resources that say, you know, one, what's it called, the decade point, from one level of pH is 1 hour. It's not as definitive of that. So it is, I guess,
and these are all
relying upon engineer expertise.
Yeah, this is again trying to cover all scenarios with one brush stroke. It's not. It's predominantly you're going to tick 99% of the boxes using a 1 gallon per hour per fixture unit, and you might add that 10 or 15% safety or diversity. So you're gonna add that, but you also have to remember that that is all of your fixture units at the same time for that 1 hour. So
Yeah.
all of your floor drains, all of your sinks. So a lot of times these are already inherently oversized or over designed. So functionally, they may that one instance of a pH of 2 is going to be able to be handled by that limestone system. Whereas if you've got something that's an industrial application that's consistently pH 2, maybe you're not going to want to go with a limestone system. You want to go with an injection system. So you have something that's a pH of 11 that's going to be dosed and injected and mixed that way. So you're not necessarily worried about your dwell time being 1 hour or 2 hours. It's more of a volume. So 15 times your anticipated GPM.
Another good question came in here. And it's one of those that I think is, you almost overthink yourself, but it's kind of the easy question that you can make complicated in your own mind. So from that sink, is a P-trap required upstream of the neutralization tank?
Upstream.
So you have your sink to the sediment interceptor and acid neutralizer. Is a P-trap required coming off of the sink?
Yes, by the definition of the code, an interceptor, or sorry, a neutralizer. I always have to caution myself when I answer this, because ultimately it's the authority having jurisdiction that's gonna make or break the decision regardless. So it doesn't matter what my interpretation is of the code, it's how it's interpreted by the authority having jurisdiction. So for example, a dip tube, you can have, let's take an example. I'm jumping around over here, but again, I'm cautious of how I answer. So a bottle trap, for example, a bottle trap isn't permitted to be used as a P-trap, but it is in a lab.
Yeah.
So essentially, a neutralization tank with the dip tube is essentially, if you think about it, it is a bottle trap. But it's the definition, if you look up definitions of a bottle trap versus definition of a neutralizer, they're completely different functionalities. One is to prevent sewer gas coming into the unit, and the other one is it's a vented system because of neutralization purposes. So that's a tough one, Zach, because if you consider a neutralizer to be a P-trap, then any P-trap upstream of that, you have a double trap. So that's the thing. So it's an interpretation. So if you're going to interpret a neutralizer to be a trap, then there's no P-trap required. Otherwise, if you're considering it or accepting it as a trap and you're putting in a P-trap, then you're double trapping.
Yeah, I guess, yeah. And for that standpoint, we would lean towards including it until the authority having jurisdiction tells otherwise.
Absolutely. Yeah.
Perfect. Well, I guess that answers all the questions unless any additionals come in. This is just like we're at the in-person lunch and learn. You know, some people have left with their food and we've got a couple of people hanging around with us.
Yeah, that's awesome. Love it. Yeah, if there's any questions, I obviously, as far as reaching out to Zach or Rebecca at ATS, or if you have my contact information as well, be more than happy to. And again, it's not a topic that everybody sees every day, so I'm happy to kind of help walk through the requirements and how things, you know, it can get confusing.
Perfect. Yeah, we'll have the contact information sent out with the follow-up to everyone. Once again, thanks again to one final question maybe coming in. Is the recording available? Yes, we will have the recording available. The link will be sent out as part of the follow-up. It's hosted on our ATS University section of the website. If they've changed the branding and I'm getting it wrong, Rebecca's going to yell at me after the call, but I do my best to keep up with all of our stuff. Once again, thanks all who joined us today. We'll see you, I guess, next week for is it next week or the week after, Rebecca? The week after for the presentation on the future of drinking fountains. Thanks again for joining us. Have a great rest of the day. Bye for now.
Rest of your day. Take care. Thanks, Zach. Thanks, Rebecca. Good to see you guys.
Good to see you.
Cheers.